In this video, we're going to be working with the fundamental theorem of algebra, which, like it sounds, is a really big deal in mathematics. But this theorem is really just something you've probably noticed already about zeros of polynomials and the degree of those polynomials. I'm just going to kind of sketch something out for you real quick. So this is the, xy axis. Now think about a degree 1 polynomial. That's a line. Okay, that can intersect the x-axis, one time, if it's going to. A degree 2 polynomial is a parabola. And it looks about like that. And remember that that could maybe intersect the x-axis up to twice. And recently we learned about y equals x cubed and other third degree polynomials, and we saw that those can kind of sometimes bend back on themselves. And so that could be the graph of a third degree polynomial, and there's up to 3 zeros. So the fundamental theorem of algebra, we're really just going to be formalizing that here. But before I get into the specifics of the fundamental theorem of algebra, I want to point out this function here, f of x equals x squared plus 4x plus 5. This is just an old-fashioned quadratic function, the type of which we studied, a while ago in this course. So if I asked you to sketch the graph of y equals f of x, I think what we did, when we were studying the parabolas, was we kind of tried to find the coordinates of the vertex first. So I'm going to work with that. And we found the coordinates of the vertex using x equals negative b over 2a, which in this case is negative 4 over 2 times positive 1. Right? If a is 1, b is positive 4, and c is positive 5. All right, so that's going to be negative 4 divided by 2 is negative 2. Okay, and then y is going to be equal to f of negative 2, which will be negative 2 squared, that'll be positive 4, plus 4 times negative 2 is a negative 8, and plus 5. So that's 9 minus 8 is equal to 1. Okay. So I've got the vertex here at negative 2, 1. And then I know that this is an upward-facing parabola because it's y equals positive x squared. Okay, and then I can just kind of draw the axes in around that. I know that a y-coordinate of 1 is above the x-axis. That's a place where y is positive. And I think that's where I'm going to leave my sketch. I could go in here and maybe I will put in a y-axis. That'll be good enough. What I want to point out is that this does not intersect the x-axis. The graph of f has no x-intercepts. F has no real roots, was something we kind of have been saying. But if I go to solve the equation f of x equals 0, we learned that we can do a little bit with this last time. Right? We can say if x squared plus 4x plus 5 equals 0, and we just follow the quadratic formula, which, by the way, is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, if I apply that formula and that square root comes back taking the square root of a negative number, it's not the end of the world. I can still work with it, right? We're just going to call it I. Okay, so I'm going to say negative b is negative 4 plus or minus the square root of b squared is 16 minus 4 times a times c would be minus 20, all divided by 2 times 1. Okay, I'll just simplify that for you real quick. That's going to be negative 2 plus or minus, 16 minus 20 is negative 4. The square root of negative 4 is 2i. So I've got 2i divided by 2 is 1i. Okay. These are my two solutions to f of x equals 0. Okay, notice how there was 2 of them, and they came in a pair. We'll have more to say about that next time. But although we had no x-intercepts, we found that we do have 2 roots of the polynomial if we're willing to look in the complex numbers. And then that's going to be kind of what we're talking about today. But there's also something else that could happen if you remember about the quadratic functions that I haven't drawn for you yet. Okay, we've seen one where there's 2 x-intercepts. We've seen one where there's no x-intercepts. We should probably talk about the one where there's 1. So that's just reminding you, the discriminant of a quadratic is b squared minus 4ac. It's the thing that goes on the inside of the square root. So if b squared minus 4ac is positive, remember we said we had 2 x-intercepts. Okay? And if b squared minus 4ac is 0, we had one x-intercept. And what that means is that we had the same one twice, right? Because it's negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, so if b squared minus 4ac is negative, I'm adding and subtracting 0 from negative b over 2a, and so it's the same number twice. And we talked about that a little bit, right? And so that's last unit, we would have called that a double root, but before we just said it was one of these quadratics that had just one x-intercept. And then if b squared minus 4ac is negative, well, we just saw what that looked like. It returned us two imaginary solutions. Okay, so just to recap, when b squared minus 4ac was positive, that caused us to have two distinct real roots, two x values that made the polynomial equal to 0. If b squared minus 4ac was 0, we had one double root. Okay, so we had one root, but it counted twice. And if b squared minus 4ac was negative, we had two imaginary roots. And I should mention that in this context, by imaginary roots, I mean non-real complex. I don't mean necessarily purely imaginary, as in they don't have any real part to the, some number plus some number of i's. Okay, I just mean roots that aren't real numbers. Okay, but regardless, in all three of these situations, kind of the number of roots adds up to 2, which is the degree of a quadratic polynomial. All right, so here it is. So the fundamental theorem of algebra. Really what the fundamental theorem of algebra is that every non-constant polynomial has at least one 0 that's either real or complex. But the related fact is what you're going to really remember as the fundamental theorem of algebra. It's that an nth degree polynomial has a total of n zeros, counting multiplicity and complex solutions. And honestly, the subtlety there, the difference between the actual fundamental theorem of algebra and the related fact, is kind of what you would study if you studied abstract algebra at the university level. So, we're kind of a ways off from that. I'm just going to relay you what the theorem is, but we're going to mostly be working with that related fact. So I just figured I'd bump it up a degree and sketch all the possibilities of a third degree polynomial for you. So I think I already showed you that we could have 3 real zeros. And I think we worked a bunch of examples where we sketched the graph and it was degree 3, but one of them was a double root. So, maybe something like that. Okay, so that had 2 real zeros, but one of them was a double root. Okay, but if we think about it, a single root plus a double root, that does add up to 3, right? And then there's another situation that we didn't graph as much, but I know that in my sections I've talked about the possibility of this happening, and we've seen this graph before, is one that only runs into it once. There's another possibility that I didn't think of. I can't believe I was almost about to miss this. Okay, so maybe I'll come back on this one here in a second. I forgot. What if there was a triple root, right? One triple root, that's definitely a possibility. So it could come up, hesitate, and then go through. And that would be one triple root, and that definitely counts as 3, right? Okay. Counting multiplicity and complex solutions. But this other one where it turns back on itself, but it only has one x-intercept. Okay, this has one real root. And what I'm telling you is that it's also got 2 imaginary roots. And I also know, I know that this is a third degree polynomial because it has got 2 relative extrema. I know it's at least a third degree polynomial. I know it's an odd degree polynomial because, the end behavior, the arms are pointing in opposite directions. But I would say most likely this is a third degree polynomial that has 1 real root and 2 imaginary roots. Okay, but that's all the possibilities for a third degree. Okay, now another example I want to work is sketching the graph of y equals x to the 4 plus x to the 3 minus x minus 1. I don't know about this. Hold on. Oh, okay. Yeah, I see where this is going. This is just going in a direction I didn't expect it to. I should have. I wrote these notes, but I guess it was a while ago. So we're going to start by doing group and factor on this. So we're going to try to factor this thing and find its zeros. So I'm going to do, okay, what's common to the first two? That's an x to the 3. And then I'd be left with an x plus 1. And then out of the second two terms, they're both negative, so I'll factor out that negative 1. And then, yeah, I'll be left with an x minus 1. Okay. And then from there, I'd factor out an x plus, x plus 1. I'd factor out, and I'd be left with x to the 3 minus 1. Okay, now, I'd say it's been just long enough that I need to remind you about a difference of two cubes. Alright, there it is, yeah, soap. Yeah, you're almost about to forget about that, right? Okay, but I couldn't let that happen. So, okay, remember, difference of two cubes is a to the 3 minus b to the 3 is a minus b times a squared plus ab plus b squared. Okay, so what we kind of got to do is identify what are the two cubes. Okay, that right there is x to the 3 minus 1 to the 3. And so this is, in the big scheme of things, not that difficult of one to factor. Okay, we're going to say that I've still got that x plus 1. Okay, and then I'm going to have x minus 1, a minus b, multiplied by, because I'm looking at a as x and b as 1. Okay, so a squared plus x times 1 plus 1 squared. Alright, and now I've got these factors. Okay, if I want to know about the zeros, I'll set it equal to 0 and say, alright, x plus 1 equals 0. Okay, I know that happens when x is negative 1. X minus 1 could equal 0 when x is equal to positive 1. And then there's this thing. Okay, that would equal 0. I'm going to use the quadratic formula because I don't think I can factor that. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, so I've got two imaginary solutions right here. Okay, and I'm not even going to really, I guess I'll simplify it. Negative 1 plus or minus square root of 3i all divided by 2. I'm not going to go any farther than that. Okay, what's important about these is these two solutions is that they're not real. Okay, and that's always going to happen with a sum or difference of cubes. I'm just going to point that out. And then, yeah, I'm going to sketch the graph, but then I'm going to say something else about that difference of cubes situation, because I'm seeing something else that I'd like to tell you. So if I sketch the graph, oh no, let's see, get that back in place. The zeros should be at negative 1 and 1. And it's a fourth degree polynomial with a positive leading coefficient, so I know that the end behavior is going to be pretty much like that. So, and x equals negative 1 and x equals positive 1 are both, single roots. So they're going to pass through the x-axis with confidence. And the same thing's happening down here. Now we also know about kind of the turning around thing about polynomials, the number of extrema versus the degree. I don't know if I actually said it in any of the videos, but we've talked about it a lot in class, that a fourth degree could turn around up to 3 times. So, it could look like that. It could just look like a normal parabola to like the tools that we have. We kind of need calculus to be able to determine, the number of times it turned around. So, it's kind of up to your interpretation. If you've got technology, you could, produce a graph of this and see that I think it does turn around, but I'm not totally sure. All right, well, there you go. Shows what I know. Okay, in a class that doesn't have the ability to do calculus, we're not going to be able to determine the number of turning around spots, but it does have a little wiggle to it, and, it has to do with the number and type of zeros, which is exactly what we're studying right now to get you ready for that type of study in a later class. All right, so this example kind of goes to the same idea. So the graph of a fifth degree polynomial is shown below. And that's, believable, at least on the basis of end behavior, because we're seeing as the graph goes to the right, it goes up, and as it goes to the left, it goes down. So I'm seeing the opposite behavior. It's what we know is going to happen with an odd degree polynomial. Number and type of roots. Okay, so I'm seeing this one right here, and then one right here. Maybe I should use a different color. It's blue. Okay, so at x equals 0, that looks to me like a double root, but I guess it could be a quadruple root. We don't really have enough information to say one way or the other. Okay, but at x equals 2, that's definitely a single root because it's changing signs, and the graph is not hesitating. So that means it's definitely a single root. Okay. Wait, not maybe 4, maybe quadruple. Okay, but we haven't really talked too much about quadruple roots in this class, and it's really not the focus here. But I should point out that it is a possibility, right? And the graph would bounce at a quadruple root. But as for a single, the x equals 2 is definitely a single root. So I guess I have to split this up into two possibilities. If the root x equals 0 has multiplicity 2, then we're going to have one double root. And a double root kind of implies that it's a real root. One single root also, and maybe I'll just say both of these are real. And then, okay, that would be a total of 3 roots that I've got, but I know it's a 5th degree polynomial, so that would mean I have to have 2 complex. Or, pardon me, I'm calling those imaginary. Because complex would probably be a misnomer as well. Because all numbers that you know of are complex numbers, right? Real numbers are part of the complex numbers. They're just, a small part of them. So 2 imaginary roots. But if x equals 0 has multiplicity 4, it's got 1 quadruple root and 1 single root, and that adds up to 5 total roots. So that would mean no imaginary roots. All right, the graph of an 8th degree polynomial is shown below. Describe the number and type of the roots of the polynomial. Okay, so this time I am going to assume that this is a double root at x equals 0. I'm not going to split this off into 2 different cases. So I'm seeing, zeros here, there, and there. So x equals 2, x equals negative 2. These are both looking like single roots to me. And x equals 0 is going to be a double root. Okay, so in total I've got 4, including multiplicity, I've got 4 roots. But this is an 8th degree polynomial, so there's got to be 4 left over, right? Because there's got to be a total of 8 roots for an 8th degree polynomial. Okay. In fact, I'm going to even write that out. 8th degree means 8 roots up to counting multiplicities and imaginary roots. Okay, so if I've got 2 singles and 1 double, that's a total of 4. I need to get up to 8. That leaves me 4 imaginary roots is what we're calling them. All right, now I'm just going to work a few more examples for you and then set you off to practice on your own. So it's known that x equals 5 is a root of the polynomial x to the 3 minus 3x to the 2 minus 50. Find the other 2 roots. Oh, yes, okay, this is a very common problem type. So what we're going to do is we're going to basically divide the given polynomial by x minus 5 using the factor theorem, and then get it reduced down to a quadratic that I bet we'll be able to either factor or use the quadratic formula on. So I'm going to go over here and I'm going to set up for synthetic division. So we're going to copy down the coefficients of the polynomial I'm dividing. 1x to the 3, negative 3x to the 2, 0 x's, and negative 50, right? Don't forget about that 0 for the missing term, that x to the first. Then we're dividing by x minus 5, 5 over here. We're just running this through. Okay, and if x equals 5 is a root, then I should, at the very end, get 0, right? That's what I'm expecting. So I'm multiplying, adding, multiplying, adding, multiplying, adding, and sure enough, I get 0. Okay, that's good news. Okay, and that means that, I can take this and write out my factors, because I've done that division. This is x minus 5 times x squared plus 2x plus 10, right? I can look at this like place value, like 1x squared, 2 x's, and 10 times 1. X to the 0 if you like that. Okay, so if we're trying to find the other 2 roots, we're trying to find the places where this equals 0. Okay, so we already know about x equals 5. They told us that. So We know x equals 5 as a root. So for the other two, I'm thinking the only numbers I know that multiply to 10 are 10 and 1 and 5 and 2, and neither one of those are going to be able to produce positive 2. So I'm going to need to use the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c, that's 4 minus 40, all over 2 times a. Okay, so all over 2. And so I'm just going to need to simplify this a little bit. It's going to be negative 2 plus or minus the square root of negative 36, all divided by 2. The square root of negative 6, that's going to be 6i. Right? Because that's going to be the square root of 36 times the square root of negative 1. That's 6 times I. Okay, so if I have negative 2 plus or minus 6i divided by 2, I got to divide everything by 2, dividing that whole addition or subtraction, I guess. And so I'll get negative 1 plus or minus 3i. And so those are my other two roots. Negative 1 plus 3i and negative 1 minus 3i. Notice those are conjugates. Okay, but like I said, we'll have more to say about this in the next lesson. Now in this one, based on the graph of the polynomial, what's its minimum possible degree? And I really think that the only thing that we can use to determine that is going to be the number of relative extrema. And so, oh no, that's not, that's better. The number of relative extrema, the number of turning around points. So we're here, 2 of these, that means we've got at least a degree 3 in it. Looks like it's got a negative leading coefficient. The minimum possible degree would be 3, based on the fact that it has turned around twice. And then this one would be minimally degree 4, because it has 3 relative extrema. Notice I'm just counting the number of relative maxima and relative minima. The next one's asking for a sketch of a 6th degree polynomial with 2 imaginary roots and a positive leading coefficient. All right, well, if I've got a degree 6, I need a thicker pen. Yeah, degree 6 with a positive leading coefficient means the end behavior will be kind of like the graph of y equals positive x squared. Okay, it'll go up on both sides. And then if it's got 2 imaginary roots, but it's degree 6, that means it's got to have 4 real roots. So, maybe you should try this yourself. Try to draw one of these that's got 4 real roots, 4 x-intercepts, and fits the bill. There's a variety of right answers. Okay, so just try it yourself. Pause the video and check against mine. It's going to pop up here in a second. All right, there you go. So I feel like there's kind of a variety of options. We could have and I think there's, some I didn't draw. There could be 1 double root and 2 single roots, and an extra turning around spot. Obviously, you could draw any of these without kind of this extra business, these turning around places that don't correspond to x-intercepts. Those, are totally optional. You could have up to that many of them, though, without it becoming, something like an 8th degree polynomial. Okay, so there's just a couple of possibilities. Okay, here's another one. So maybe on this one, I'm envisioning no imaginary roots. So that means I have to have a total of 5. Okay. So 5th degree means 5 total roots. None of them are imaginary, means they're all going to be real. So I could just, and a negative leading coefficient, okay, well I need to respect that end behavior and just make sure it comes from above and then eventually goes down on the right. It said I could have up to 5, so it could be 1, 2, 3, 4, 5, like that. Okay, no, it wouldn't have to be. I could say maybe it's got a triple root. Right, it could come down and have a triple root, and then 4, 5, right? That could have been a double root, think about it, if I had just kind of turned it around at the x-axis. Okay, that would have been 5 total roots. That would be just as valid of a sketch. Okay, let's see, 5 total. I could have 2 double and 1 single. That would add up to 5. So, double triple, single, double, or any order you like. There's all sorts of ways you could draw this. Those questions make for really good like discussion and partner work in class, but maybe not as not as great at home. This will be great for you at home. I'll help you practice your skills. We're going to find the values of x that make the equation true, but I think you should try this on your own, right? We're going to set to 0 always. Try to factor if we can, and if we can't, use the quadratic formula. And because we've been talking a lot about complex numbers, I would expect to use the quadratic formula and have it come back with some eyes, right? But try this one on your own. Pause the video because my answers are just going to pop up here in a second. All right, there you go. So, on these, just like with any other polynomial equation that we're solving in this class, gotta start off by setting the equation to 0. Okay, that's really the key here. That unlocks all the possibilities. We can either solve by factoring or quadratic formula or whatever we're going to do, but it all starts with setting the equation to 0. Okay, so I did that on both of them. The one on the right in green, that was able to factor, but then they both ended up having the quadratic formula. The quadratic formula actually ended up working out very similarly, kind of, I think by coincidence, and that's what I got. All right, so I think that's all the examples. Let me check. Yeah, that's going to be all the examples I'm doing for you. I think now it's time for you to practice on your own. So, yeah, good luck with that, and thanks for watching.